Now it is chapter 15, finite element methods for boundary value problems. You may try to watch FM songs in the beginning of the chapter. Currently, the two songs include only melodies with lyrics, which show core concepts of finite element methods. Later on, of course, I'll add some videos. Okay, you can click to listen to the songs. One is in rap, the other one is on rock. Okay, let's go to first section of the chapter, variational principle from strong form to weak. Let's see what they are. Consider approximating the solution to a two-point boundary value problem in this form. Here, P is continuously differentiable function of x and positive. The boundary at boundary from 0 to 1 and left edge point, the function value is 0, and also at right edge point, again, the function value is 0. For simplicity, we start with this simple problem. It is called the differential problem. The FEM is formulated with the so-called variational principle. So we'll begin in the section variational principle. It starts with a linear space. We define a linear space over the interval, the given domain. The collection of function, now it's continuous. C0 means just continuous function over the interval 0 to 1, and its derivative is piecewise continuous. And finally, at edge points, the value is 0. So such functions, collection of such functions is a vector space. So we call it a linear space. Now we multiply a test function from this linear space and the equation. That is now in another form, rather than here derivative form, we are using prime notation, minus pu prime prime, and v, both sides, v is multiplied. V is from the linear space. Now, we integrate both sides, and then from the left-hand side, we see here, and by using the integration by parts, we reach at this one, and then another one here. I guess you learned this one from calculus 2. Now, for this term, we need to evaluate this term at 0 and at 1. But from the beginning, we chose v such that from inside the space, the value at boundary points are 0, so that this will disappear, and we have only this term. So the right side integration, and put together, we have this form. After multiplication of a test function from the vector space and integrate over the interval to get this Euc form. Of course, we use the integration by parts. So that is Euc form. Then the original equation is strong form. From strong form, by using this test function integration by parts, we reach at this Euc form. Now, to deal with this equation more effectively, we introduce bilinear functional and linear product. Okay, that one, B, UV. Just we call this term B, UV. We may consider this one as a function of U and as a function of V. So it is a bilinear, but linear function. So it's a bilinear function. And then now that is a simple linear product or inner product between f and v in this way. Okay, we define these two terms by using these notations. Then, now, we can define the variational problem corresponding to the given differential problem. Now, we'll try to find u from the linear space V such that now this equation is satisfied for every choice of V from the linear space. In fact, this one is the same as this equation, assuming that now the solution is second order differentiable, then we can go back to original one so that this one is almost the same as the original problem. Now we are trying to find u inside the linear space, satisfying this one for every choice of v from the linear space. Now we have a theorem. The differential problem, which is given and in its strong form, is equivalent to the variational problem when the solutions are sufficiently smooth. From differential problem to variational problem is quite clear. We start from the strong problem, strong form, and test function multiplied and integrate, integration by part, and we reach at this equation, so that is quite clear. How about the other direction? Now we start from variational problem and try to reach at the differential problem. Let's consider u is a solution of the variational problem. Then, now, this equation will be satisfied for every choice v from the linear space. Now we assume u double prime exists. Then this portion, now we try to do integration by part and reverse the direction. Then now there will be 0 and we reach at this term. So that, and the right side, this one is same as this one, and we reach at this equation. So we move this to the other side, and then we end up with this one. Now, a function times another one, but every choice of this v, the integration is 0. That means that this must be 0. If it is 0, then that is exactly the equation in the strong form, the differential problem. So here equivalence means that these two problems have the same solution. Okay? Now we'll try to define minimization problem. Here we define functional given in this form. Now f of v is f, and there is the same v, b vv minus fv. We define the minimization problem. We try to find u from the linear space such that f of u is minimum among all possible value for v chosen from the linear space. So that is the minimization problem. by using some calculus technique, we can prove that the minimization problem is equivalent to the variational problem. Now, here, another theorem is saying that the variational problem admits a unique solution provided the condition is satisfied. That is, the positiveness condition 15.2. Let's go back over there, that one. So that the diffusion coefficient is positive, strictly positive everywhere. Then here we can prove this theorem, and the variation problem admits unique solution under the condition satisfied. That means under the same condition, here the minimization problem admits unique solution. So we summarize what we have done. Differential problem, variational problem, and minimization problem, they are all equivalent by assuming that U double prime exists. And these two are basically the same. Now, D implies V, but the other direction is requiring that condition. Also, here under the condition, that one, positiveness condition for the diffusion function, these problems admit unique solution, which means that solution from here, 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 all are the same and unique. We have a final remark. Strong form versus weak form and finite element method. The strong form represents the original differential equations and boundary conditions describing the physical problem. The weak form is an integral formulation derived from the strong form, so that eventually it is relaxed to allow for more manageable numerical approximation. Now, I'll try to explain this one. If you deal with the strong form, then, okay, let's go to over there. Looks like you have to deal with second derivative, so that the existence of second derivative must be given. However, if you go to weak form, then only first derivative is involved. So that rather than strong requirement in regularity, the conditions are relaxed and we can deal with the problem more easily. Okay. Now the finite differential method, finite element methods find numerical solutions from the weak form, so that the method makes the problem more amenable to numerical solution and reduces smoothness requirements, and also facilitates the handling of complex geometries and boundary conditions. We'll deal with only one-dimensional problem. However, if you try to solve high-dimensional problem like 2D and 3D, in many cases, the geometry is not really rectangle, so that very complex geometry can appear. When it happens, then you have to choose finite element method to get the solution more flexibly. Okay, that's the end of the section. Thank you.